Hi, Dr. Lane. So I'm doing a reassessment for Chapter 4, and I kind of included bits and pieces of every single concept that we covered on the assessment. So the first question I did was to find the diameter of a problem because I know I messed up and that was a arithmetic issue. So I chose a problem out of the book, and it was from Chapter 4. Number 27, and it reads 1 mole of tungsten, which is 6.202 times 10 to the 23rd atoms, has a mass of 184 grams as shown in the periodic table on the inside front of the cover of the book. The density of tungsten is 19.3 grams per centimeters cubed. What is the approximate diameter of tungsten atom in a solid block of the material? Make the simplifying assumption that the atoms are arranged in a cubic array. So it's very similar to the one we did on the assessment. So I take the density and I multiplied. I try to get the units to kilograms per meter because that's what we can work with. So I multiplied by 1 kilogram over 1,000 grams times 100 centimeters over 1 meter, and then everything's cubed. So that would give me 19.3 times 10 to the third kilograms per meters cubed. And now I take that value and multiply it by the given number of, well, I changed my grams to kilograms, and then by number of atoms. So I take 19.3 10 to the third kilograms divided by meters cubed times 1 mole of tungsten over 0.184 kilograms. So I did the conversion. I moved it over 3 decimal places to the left to get kilograms, and then times 6.02 times 10 to the 23rd atoms over 1 mole. And that's going to give me 6.314 times 10 to the 28th. Now, because as I told us to assume that it's a cubic array, one of the edge of the cube is going to be 1 meter. So we have to take the cube root of that because right now we're in meters cubed. So if we take the cube root of 6.314 times 10 to the 28th, we get 3.98 times 10 to the 9. And since a row of atoms is 1 meter long, we have to do, I guess you call it the inverse, so it's 1 over that value. So it's going to be 1 over 3.98 times 10 to the 9th, and that's going to give us 2.511 times 10 to the negative centimeters, and that's the diameter of the tungsten atom. Okay, now the second problem I did from the book was from chapter 4, number 42, and this one reads, 2 wires are made of the same kind of metal. Wire A has a diameter of 2.4 millimeters and is initially 2.8 meters long. You hang an 8 kilogram mass from wire A, measure the amount of the stretch, and determine Young's modules to be 1.37 times 10 to the 12 newtons per meter squared. Now wire B is made of the same kind of metal as wire A, has the same length as the wire, but twice the diameter. You hang the same weight from wire B, measure the amount of stretch, and determine Young's module. So I did what you told me to focus more on the concept instead of just the numerical values of this one. Obviously, you wouldn't have to plug in anything. I mean, I did, and I have it here once again. I know it's kind of backwards, but I could show it to you if you needed me to. So we have the formula for Young's modules, which is F over A, everything divided by change of L over L. So we know the diameter and everything of wire A and wire B. Now, I said that the Young's module values for the wires are going to be the same. Now, the reason I said that is because although the second spring has a bigger diameter, it's made out of the same material, so it's going to stretch essentially the same amount. So it's going to be in equal ratio to one another. And you could have I could have proven that numerically as well if I was given the amount of stretch um, of the first wire, honestly of both wires, because I needed that. I had everything else. I had the diameter, well, radius to figure out the area. Uh, I had the length, the mass. So I just needed. I could have put the mass times gravity in to get the force. I just needed the stretch, and the same thing for B. I needed the stretch. So if I could have gotten that, I could have plugged everything in just like we did on the assessment, and essentially gotten the answers. So that's why they're the same. Um, and now the third problem I did, which is also kind of like focused more on the concept, was problem 32 from chapter 4. And it says you hang a mass M from a spring which stretches an amount. No, I'm sorry. 32. Spring has stiffness Ks. You cut the spring in half. What is the stiffness of a half spring? So stiffness is the rigidity of an object. And we kind of discussed this in class a lot. If you would cut it in half, the stiffness of it would increase. The shorter it would get cut, the stronger it would get. It's just like in the other problem. I know we didn't cut it or really add anything, but because the diameter increased, it became weaker. That's why it stretched longer than the first spring. So the same thing here. If you would cut it in half, which is essentially doing the opposite, it would stretch even less if you would hang something from it. So the answer that I put for number 32 would be A, 2 ks. So the spring would double. So that's all I got. If I need to fix anything, just let me know. Thank you.